Welcome back to The Explainer. Today, we are diving into a surprisingly complex, deeply fascinating, and honestly, heavily relied upon piece of technology. We're talking about the world of alternating current synchronous systems. Now, you might have heard these referred to by trade names like autosyn or cellsyn, but if you've ever stopped to marvel at how those intricate analog flight instruments function flawlessly thousands of feet up in the air, well, you are absolutely in for a treat today.
So, here's a question for you. How exactly do airplanes transmit complex mechanical movements over long distances without relying on digital computers? I mean, it's a fantastic engineering puzzle, right? Before modern microchips were even a thing, engineers had to figure this out using pure physical ingenuity. And their answer? These analog synchronous systems, or synchros for short. These were the ingenious mechanical problem solvers that made sophisticated flight instruments possible. They literally copied and calculated movements across the entire aircraft using nothing but wire and magnetic fields.
Here is our roadmap for today. First, the core physics. Second, the basic synchro, or torque. Third, the error corrector, which is control. Fourth, the angle calculator, or differential. And finally, number 5, the coordinate converter, the resolver.
Okay, Section 1. The core physics, electromagnetic induction and transformers.
Okay, let's dive into this. To really wrap our heads around how any of these analog systems work, we've got to start with the bedrock physics. And it all begins with electromagnetic induction. Simply put, this is the production of an electromotive force, basically a voltage, within a conductor whenever there's relative movement between it and a magnetic field. But what's really wild about this is a phenomenon called mutual induction. If you take two current-carrying coils and just place them near each other, they become linked by the magnetic fluxes they're producing. So if you change the current in one, you magically induce a voltage in the adjacent coil, and they don't even have to touch.
You can actually see this exact concept in action with a standard transformer. On the left side, you've got a primary winding connected to an alternating voltage supply. Now, this AC supply creates an alternating magnetic flux right inside that laminated iron core. And because that flux links up with the secondary winding over on the right, it induces a voltage in that secondary coil purely by mutual induction. Literally, all the energy is transferred magnetically right through the core.
So the real secret sauce here is how we manipulate this transfer of power. And that all comes down to the turns ratio. The voltage in these coils is directly proportional to the number of wire turns, meaning if the secondary coil has more turns than the primary one, your voltage goes up. But check out that bottom row. The electrical currents are actually inversely proportional to the number of turns. This specific relationship is exactly what gives us the ability to precisely control electrical signals. And that is exactly what we need to build a synchro.
Moving right along to Section 2, the basic synchro, or torque, copying movement over distances. So, let's see how this builds into something genuinely mechanical. Think of a torque synchro as basically a rotating transformer that acts like an invisible, completely flexible mechanical shaft connecting two dials. Take a look at this classic system setup. Over on the left is your transmitter, or TX, and it's mechanically coupled to an input shaft. On the right, you have the receiver, or TR, connected to an output shaft. Notice how their stators, those are the outer windings labeled S1, S2, and S3, they are wired directly to each other. When both of those rotors perfectly align with their stators, we call that position electrical zero. It's essentially a standardized reference angle. Everything is in perfect balance, and absolutely no current flows between them.
But what actually happens if we twist that input dial? Let's walk through the exact chronological action here. Step 1. The transmitter rotor moves, which immediately misaligns the system from that electrical zero. Step 2. This creates a voltage unbalance between the stator coils of the two units. Step 3. That unbalance forces actual current to flow right through those transmission lines. And finally, Step 4. That current produces magnetic fields in the receiver that exert physical torque. It literally forces the receiver's rotor to perfectly mimic the transmitter's movement until the whole system is balanced again. It's perfectly copying physical movement across a distance. No digital code required.
Which brings us to Section 3, the error corrector, or control, steering with signals.
Now, torque synchros are awesome for moving lightweight things, like little dials. But if you need to move something heavy, we're talking about things like a central air data computer, we have to use a control synchro. Here, we've got a control transmitter on the left and a control transformer, or CT, on the right. Notice a really crucial difference here, though. Unlike our previous receiver, the CT's rotor is not connected to an AC power supply. So instead of acting as a magnet that just gets pushed around, the CT rotor acts purely as an inductive winding. It's basically a detector, just waiting there to sense any kind of misalignment.
So how does this version work? Well, first, the input shaft rotates the transmitter. Second, this shifts the magnetic flux over in the control transformer, which induces what we call an error voltage, right there in that unenergized rotor. Third, instead of trying to use weak magnetic torque to muscle a heavy dial, it takes this tiny error signal and sends it out to a powerful amplifier. And finally, that amplifier commands a strong external two-phase motor to physically drive the entire system back into alignment. It is literally steering heavy machinery using nothing but delicate magnetic error signals.
All right, section 4, the angle calculator or differential, adding and subtracting mechanical inputs. This right here is an absolutely incredible analog method for mathematically combining two entirely separate mechanical inputs, again, without a single line of digital code. To pull this off, engineers insert a third unit right dead center into our standard system. Look at that unit labeled TDX in the middle. It has identically wound stators and rotors. By dropping this directly between the transmitter and the receiver, it intercepts and modifies the magnetic fields traveling between them based entirely on its own physical position. Because of the way these magnetic fields interact, changing the position of that middle rotor fundamentally shifts the baseline for the receiver. The real takeaway here is that depending on exactly how you wire the pairs of leads between these units, this system will literally output the physical mechanical sum or difference of the two input shafts. Think about it. You input 60 degrees on the first dial, you put 15 degrees on the second dial, and the receiver just automatically snaps to 45 degrees. It is quite literally an analog calculator.
And now, section 5, the coordinate converter, or resolver, analog math computers. We have finally made it to the absolute pinnacle of this analog technology, the resolver. The resolver goes way beyond simple addition and subtraction. It performs continuous trigonometry. The magic behind this rather complex 8-terminal setup relies on a concept called phase quadrature. Unlike those earlier synchros that use 3 coils spaced 120 degrees apart, the resolver uses 2 stator windings and 2 rotor windings, and they are deliberately arranged exactly 90 degrees apart from each other.
So what does physically separating things by exactly 90 degrees actually do for us? Well, because they are exactly perpendicular, the alternating flux induces varying voltages based directly on the rotor's physical angle. Specifically, the voltage across one winding naturally rises and falls to directly measure the cosine of the displacement angle. Meanwhile, the other winding is simultaneously outputting a voltage that's directly proportional to the sine of the displacement angle. It's basically doing geometry in real time. And this brilliantly illustrates exactly why that is such a game changer. If you use the resolver in reverse, say taking an alternating voltage that represents an x coordinate and feeding it into the cosine winding, while feeding a y coordinate voltage into the sine winding, they combine inside the stator. This creates a highly specific magnetic field that forces an attached servo motor to physically rotate to the exact polar angle, all while outputting a voltage representing the precise radius. Bam! It is instantly converting Cartesian coordinates into polar coordinates.
So, let's take a quick step back and summarize the 4 incredibly clever branches we've explored today. Torque synchros directly copy physical movement for your basic dials. Control synchros use error signals to steer heavy lifting motors for things like air data computers. Differential synchros mechanically add or subtract angles. And resolver synchros, they do continuous trigonometry to convert coordinate systems for complex navigation. Every single one of these solves a completely unique problem just by manipulating the elegant physics of electromagnetic induction.
Which brings us to a final thought I want to leave you with today. In an era where absolutely everything is heavily digitized, can modern digital systems truly match the instant, continuous, and elegant reliability of these analog marbles? I mean, there is a profound, almost beautiful mechanical genius in achieving continuous, flawless mathematical conversions and physical synchronization without a single microchip in sight. The raw power of analog engineering is truly something to marvel at. Thank you so much for joining me on this explainer, and honestly, I hope you never look at a mechanical instrument dial the same way again.